So this is equation 61. There will be another large matrix involved in the question. Unfortunately, unfortunately in terms of writing, many questions in this chapter, especially towards the end of the set of the questions, they use the higher dimensional examples, and that's one of them. So we're going to look at the matrix A, which is rather big. That's the matrix with the, I think it's a 1, 2, 3, 4, 5 by 4 matrix. It is a 5 by 4 matrix, and I will write this matrix once. I will open this matrix once. Here it is. First row 1, 1, 0, 2, 1. Second one 0, 0, negative 1, negative 2, 2. Third one is negative 1, negative 1, 1, 4, negative 1. And the last one is 1, 1, 0, 4, and 2. We're going to discuss the concept of the column space of the matrix A. And even though maybe it's the first time you hear this concept, column space of the matrix A, in fact, we actually discussed this already under a different name. Column space of a matrix A, and that's the symbol which we use for that. Col of A. Look what it is. That's the collection of all vectors, four-dimensional vectors, and in fact, I use the letter F here because what I'm saying is applicable to three instances. F may be either rationals, reals, or complex numbers. Everything I say will be applicable equally to all of these three different settings. That's why I use the letter F for the field of scalars. So it's all four-dimensional. It's a collection of all four-dimensional vectors, which are a result of the multiplication of A by a vector X, which happens to be five-dimensional because we have 5 columns in this matrix. Something like this we discussed with you, actually. We have discussed this with you on a few occasions. And in fact, on one occasion, we identified this column space with a span of S, where S is a set of vectors formed from the columns of my X. So if this is my X1, this is my X2, X3, X4, and X5 vector, which simply the columns of my A. If I take them as vectors, and if I take the span, that will be the same column space. That's why I told you, even though it's a new name, we have discussed this concept in principle before, a few times already. So it's not a name to remember, another notation to remember, but it's an object, in fact, which we met already a few times. So in equation 61, we need to find the basis for this column space of the matrix A. And again, it's a method which relies on the row echelon form. Again, I'm not going to just compute the row echelon form by hand. I use the computer algebra system for that. It will be rather lengthy and a rather large row echelon form, but that's the last one for today, I promise. Here it is, 1, 1, 0, 2, 1, it's just the first row. 0, 0, negative 1, negative 2, and 2. 0, 0, 0, negative 2, and negative 1. And the last row is full of zeros. So this is something we did with you 2 days ago. When you take this matrix to the row echelon form, you can now identify which of these 5 actually represent linearly independent subset. You have to choose those vectors which correspond to the leading columns in your row echelon form. And my leading column is the column number 1, column number 3, and column number 4. So out of the same set, out of the set S, in fact, the set B, first, third, and the fourth vector will be linearly independent. And it's a lemma which we proved with you, actually. We proved this lemma with you 2 days ago. The span of the smaller set will be the same as the span of the original set. We proved this with you, that if you're dropping out these solutions, if you're dropping out the vectors from the linearly dependent set, the span will not be altered. until you reach the smallest linearly independent subset. And here it is. In that case, it is this one. So in the light of our new definition, I can say that B is the basis for column space of A, because on one hand, B spans column space of the matrix A. On the other hand, B is linearly independent. You see, B spans it, and B is linearly independent. So B is in fact basis for the column space. And the question 61 is finished. We found basis for the column space of the matrix A.